Hi, Mrs. O'Reilly here to talk to you about energy and heat from Unit 3B. Taking a look at our focus, we're looking at topics like kinetic and potential energy, endothermic, exothermic reactions, how that relates to bond breaking and forming, potential energy diagrams, law of conservation of energy, combustion, heat of combustion, and specific heat capacity. To start, we're going to talk about energy and fossil fuels. Fossil fuels include things like petroleum, coal, and natural gas. They are nicknamed buried sunshine. This is because the energy that we find in the chemical bonds of coal ultimately came from plant life from millions and millions of years ago. These plants were in swamps, and they got their energy through photosynthesis from the sun, and that energy, which came from the sun, was buried beneath layers and layers of sediment, and in some cases water, and turned to coal under all that heat and pressure. So the sunshine was buried, and now we have coal. So we call it buried sunshine. Two main forms of energy that we're going to talk about are potential and kinetic. Potential is stored energy, and kinetic is motion, energy of motion or movement. An example, we're going to focus primarily on potential energy. An example of potential energy is chemical energy. It's the energy stored in a chemical bond. So when you think about potential energy, you can think about a wind-up car or a wind-up toy car. You turn the crank and you get all that energy inside of the toy car, and it's stored in there until you let go. Once you let go, that stored energy becomes motion or kinetic energy, and now it's doing a job. So similarly, inside chemical compounds, there's energy in those bonds. And when those bonds, those substances undergo combustion and those bonds break, we can release that chemical energy in the form of heat. And we call it thermal energy. And that heat is then able to be converted again to be used, or we can use it as heat to heat our homes, a variety of reasons. And we're going to get into that a little more. So when we look at energy and chemical reactions, we're looking at a diagram like this. So you think about this methane molecule is going to undergo combustion, and when that hydrocarbon goes through combustion, it's going to react with oxygen. What's going to happen is it's going to happen in two steps. So this chemical reaction starts with the first step where the original bonds are broken. This requires energy. You need energy to break apart those bonds because those atoms are attracted to one another, and that's what formed the bond to begin with, an attraction. So it's going to take energy to break that attraction apart. What happens then is you have all these atoms in this very, very instantaneous transition state or an intermediate state. And then step two happens. Those separate atoms then reform and form new bonds in a different arrangement, forming new molecules. And this is a process that releases energy because these individual atoms don't stay like that for very long because they're very unstable. And now they're much more stable as products in the new molecules because their energy levels are full and they are happy and stable in that environment. So we look at this in terms of absorbing energy and releasing energy, and we talked about that. So this first step, this breaking bonds, actually requires energy. We call that endothermic. Endo meaning inside, thermo meaning heat, and that heat is going into the system. It's absorbing energy. When we release energy, we call that exothermic. That exo means outside, therm means heat. That heat is going outside or being released to the environment. This happens when bonds form because the atoms become more stable and have less energy than that intermediate state. And we use an energy diagram, or it's a type of graph, to show this. These energy diagrams look like this. The one on the left is for an endothermic reaction, and on the one on the right, it's exothermic. They have a lot of the same components. They all start with the energy of reactants, and as the reaction continues, you end with energy of the products. The y-axis on both graphs shows energy. So let's take a closer look at endothermic. The energy of the reactions is very low on that y-axis, meaning it has a low amount of energy. Overall, energy is absorbed, and now the products have more energy than the reactants. So there's an overall increase in energy. That's that energy going into the system. That's that endothermic. but it shows this extra bump in the middle. That's that transition state from the last slide. So that those reactants require this incredible amount of energy called the activation energy in order to break those initial bonds. Then at the top of that peak, you have the transition state. Then you see a decline in energy as new bonds form and the products become. This is where they are more stable, so they have less energy than that intermediate state. But in an endothermic reaction, you're going to see an overall increase in energy from the reactants to the products. Exothermic is the opposite. You're going to see an overall decrease in energy from the reactants to the products, showing that energy is released. You're still going to see that activation energy where bonds are broken. You're going to see that peak for the transition state, and you're going to see that decrease in energy for products to form as the new bonds are formed and the atoms become more stable. All the same components, but the big takeaway here is exothermic has an overall increase in energy, and endothermic has an overall increase in energy, and exothermic has an overall decrease in energy. When we look at energy conversion, we have to look at the law of conservation of energy. So it sounds a lot like the one for matter, but the law of conservation of energy says energy cannot be created nor destroyed, but it will be converted into different forms so that we can use it. An example I'll walk you through is taking fossil fuels and converting that energy into heat that comes out of a hairdryer. So we start as fossil fuels, which has chemical potential energy. That stored energy is inside the chemical bonds. By burning that fuel at a power plant, it undergoes combustion. That combustion releases heat energy, which is thermal energy. That thermal energy heats water. That water turns to steam and turns some turbines. Those turbines, because they're moving as a gear, is considered mechanical energy. That mechanical energy then spins the turbines inside of a generator. That generator creates electrical energy or electricity. That electricity travels through the power lines, out your outlet into your hairdryer, where it's then converted to heat or thermal energy to dry your hair. Automobiles also convert energy multiple times. Originally, it can be powered by gasoline, electricity, or solar. So those are the original energy sources that can go into the automobile. And it will be ultimately converted through steps to get it to mechanical energy so the tires spin and your car rolls down the road. Energy efficiency is dependent on how many different conversions, so every time there's an arrow, how many conversions in the process. The more conversions there are, the less efficient the process, because with each conversion, some energy gets wasted through thermal, light, or sound, so heat, light, or sound. Petroleum and gasoline goes from chemical to thermal to mechanical and is typically less than 50% efficient. We have some promise for the future with solar and fuel cells, which each only go right from their source directly to electrical. So again, those fewer conversions will lead to a more efficient process. So the amount of energy that you start with in that original fuel source, energy source, will then be the comparison to how much energy you get out at the end of that process. And so the more energy you get, the higher percentage of that original energy you get, the more efficient that process is. Combustion has to do with specific heat capacity. So every different substance takes a different amount of energy to heat it up. So water has a high specific heat. You got to put a lot of energy in to heat it up. Metals tend to have lower specific heats. You can heat them up a little easier. You don't have to apply as much heat. We use heat of combustion as a measurement of how much thermal energy is given off when certain things burn. And we usually use moles for calculation. So you're going to hear it called the molar heat of combustion. So I know we love that term, moles. We can alter fuels to meet our needs. So one way is through cracking. We can take these really large hydrocarbon molecules and convert them into smaller ones by heating them up. We use catalytic cracking for this. So a catalyst is something that increases the speed of reaction. It participates in the reaction, but doesn't get used. It just kind of hangs out on the side and says, hurry up, guys, hurry up. And it speeds up the process. So catalytic cracking is actually more energy efficient because it can occur at a lower temperature. So you don't have to apply as much heat to split apart those long hydrocarbons. And this is just a diagram showing a long hydrocarbon cracked into 2 shorter hydrocarbons. So you have a 6-chain hydrocarbon or hexane split into a 2 and a 4-chain. And that's ultimately what you're doing. And you can use those products now for a different purpose. Another way is the octane rating. This is determined by comparing the burning efficiency of a fuel when it's a free running engine versus when it's under a load, like when it's towing something like a boat or a trailer, or it's passing, so you're accelerating, and then you take those results and you average them. Higher octane ratings mean that you have a better anti-knocking characteristics. It just means it's ultimately going to prevent engine problems in the future. And knocking or pinging is caused by premature burning, so when it happens early. And it happens when the pistons bang backwards against the crankshaft at the wrong time, and ultimately you can get some engine problems from this. The isomer of octane has really excellent combustion properties in automobiles, and we call that isooctane. And we base off the octane rating, this 87, 89, and 91 on the fuel pumps at the gas station. That's the octane rating. It's based off of a comparison where this isooctane is the very best, that would be 100, and we compare it to a fuel that's very poor, which is a straight chain heptane, so 7 carbons. And where it falls on that scale is the number it's given, the 87, 89, or 91. It just says how efficient that energy burns. Another way is oxygenated fuels. Basically, we add in some oxygen into it so it has a cleaner burn. These are additives that are blended with gasoline. It used to be lead, and now we know it's no longer safe, so we don't use that anymore. And it lowers the emissions of air pollutants, so it's a cleaner burn. And that's a cleaner burn because there's more oxygen available. You get more carbon dioxide rather than carbon monoxide in the combustion reaction because of that. So just to recap, energy, we're looking at 2 main ideas: kinetic, which is moving energy, and potential, which is stored energy. So those are the 2 main types. Endothermic and exothermic reactions talk about where the heat is being transferred. Endothermic is it's being absorbed into the system, and exothermic is the heat is released into the environment or the surroundings. We know energy cannot be created or destroyed, but it can be transferred or converted. We look at heat in terms of heat of combustion and specific heat capacity. And we know usable energy comes from heat that's released from the combustion of hydrocarbons. We know fewer energy conversions will ultimately lead to a more efficient process. So we want fewer conversions in our processes so that we have a cleaner burn and a more efficient process, get more of the original energy in the output. As always, send your questions to me through email or through Google Classroom, and I'd be happy to answer them. Thanks.